Hello and good day, everyone. We are from SKEE3533 Communication class, Section 3, Group 1. So, we will talk about pulse code modulation or called as PCM. This is how PCM, pulse code modulation, works. So when we receive the analog signal, it will go through three stages. The first stage is sampling, and then after that, we undergo quantizing, and then in the end, we go through encoding, and the output for this system, we will get a digital data. Basically, PCM or pulse code modulation is a process of converting analog signal into digital signal. So as I mentioned just now, the analog signal will go through three stages. First, go through sampling, and then go through quantizing, and in the end, go through encoding, and the outputs will be a digital data. Now we will discuss about the first stage of PCM, which is sampling. So sampling theorem or Nyquist theorem is the process of measuring the instantaneous value of the continuous time analog signal and to convert it into digital form. There are three types of sampling method: ideal sampling, natural sampling, and flat top sampling. Here discuss about the sampling rate. So sampling frequency Fs is equals to 1 over Ts. Ts is the sampling time, Fs is the sampling frequency. Nyquist rate is a rate of sampling that the signal sample without loss or overlapping. So it has a condition whereby the sampling frequency must be more than 2 times Fmax. This Fmax is from the analog signal, and this Fs is the sampling frequency. So for popular sampling, all the sampling needs to fulfill the condition of the Nyquist rate, which is Fs must be more than 2 Fmax. So here there is a popular sampling. As you can see at the left, Fs equals to 3 Fm. So how does this 3 value get? You can just see from the signal itself, from the analog signal, you can just see from one cycle, we take 3 sample. This, the black square box is the number of samples that we take. So in one cycle, just one cycle, you can see that there are 3 black box. And then for the next cycle, there is also 3 black box. So this is how the 3 we got. And then the example at the right is a improper sampling because it is Fs equals to Fm. So Fs equals to Fm, which means that in one cycle, you only take one sample. So in the end, the sample will be improper and it might cause distortion or overlapping between the signals. So this is the difference between proper sampling and improper sampling. Sampling process basically goes through a modulation whereby the message signal MT will goes through a pulse signal ST, and then they multiply together in order to get the sample signal MS. The pulse signal, the Fourier series for the pulse signal is given with this formula: ST equals to tau over Ts plus 2 tau over Ts summation of n equals to 1 to infinity sinc n pi tau over Ts cos 2 pi nt over Ts. This is the formula for the pulse signal. Here is the mathematical expression of Ms, the mathematical derivation of Ms sample signal. So as we discussed before, Ms equals to Mt times St, message signal times pulse signal, and we have the Fourier series of pulse signal. So we multiply Mt to it, and in the end, we got ms equals to this expression, the one at the last sentence. Mst equals to cos omega mt tau over ts plus cos omega mt tau over ts summation n equals to 1 until infinity 2 cos n omega st. Here is how we continue to expand the expression. So in the end, we will expand the expression until ms equals to tau over ts and terms of cost function. So after sampling, we will have a lot of samples, and then these samples will have different amplitudes. However, digital systems can only store finite and discrete numbers. So therefore, the next process after sampling is called quantization, which is basically change all these uh, amplitudes to the nearest discrete value for the digital system in order to read them. Usually, when we talk about quantization, there are three common terms that we usually talk about, which are quantization level, quantization interval, and quantization value. So, let's talk about quantization level first. Quantization level is basically just how much discrete value that you want to insert based on how much sample you made in sampling the continuous amplitudes. And then quantization interval is basically the magnitude between two intervals. Let's say between 110 and 101. How much is the magnitude between them? And middle voltage for each quantized level is the quantization value. Quantization value will be explained further later. So this is the explanation for quantization level. Quantization level is given with the term L equals to 2 power n. And then n is the number of bits. Basically, is the number of bits that you use in order to represent the discrete value that you want to use for the digital system to store the amplitude for each samples. So now let's say we have n equals to 3. We have 3 bits. So the quantization level will be L equals to 2 power 3, which is 8. So this means that we will have a total of 8 levels. As I said just now, we have n equals to 3. So we have 3 bits. So basically we start with 0, 0, 0, 3 bits. 0, 0, 0 is level 0, and then the next level will be 0, 0, 1, and then continue all the way until the last level, which is 1, 1, 1, which for this case is level 7, and total up we will all have 8 levels of quantization level. So after we know the quantization level, we need to know how much voltage is inside each level within their range. So this is called quantization interval. It is given with the formula of Vmax minus Vmin over L. So let's say for example, like the previous question, we have 8 quantization levels. This means that we use 3 bits. And now, let's say the sample that we take from the sampling, we have the amplitude of the sample voltage is 5 volt. This means that the peak to peak voltage will be 10 volt because the amplitude is 5. So they calculate the quantization interval. So we will take 5 minus negative 5. Negative 5 is the V mean, and then over 8. 8 is the L, which is the quantization level. So after that, we will get 1.25. So this will be the quantization interval. That means each level, the interval voltage between them is 1.25. So after we know the quantization interval, we already know the range of voltage within each level. So now the next thing is we need to find the quantization value, the actual voltage value for each level. The reason why we need to find this quantization value is because Usually for digital systems, when we want to when we want to insert any voltage, we cannot just tell them a range. Let's say we cannot tell a digital system to input voltage between 1 and 2 volt. We need to give them actual value. So that is why for this we need to find a quantization value, which is the actual value within each level. So let's say now, like the previous example, let's say level 0 has range of negative 5 volt to negative 3.75 volt, and then with the quantization interval of 1.25. So now we want to find the quantization value at level 0. So the quantization value is just simply just take negative 5, take the lower limit, and then plus 1.25 over 2, plus the interval over 2, because quantization value is the middle voltage. We take the middle voltage within each range. So after we get is negative 4.375. If we want to use it the other way, we want to calculate the other way, we can also take negative 3.75, you minus 1.25 over 2, and then you will also get the same answer. Just that here it shows the calculation is take from the lower limit. So therefore it will, if you take the lower limit, you need to plus the quantization interval over 2. If you take the upper limit, then you need to minus the quantization interval and then divide by 2. And then you will get the same answer. So for this example, the quantization value for level 0 is negative 4.375. As you can see, this value is within the range of negative 5 to negative 3.75 volt. So just now we are discussing about the quantizing process. So all the three terms, quantization level, L, quantization interval, and then quantization value. So in the actual quantizing process, there are two types of process, which is uniform quantization and non-uniform quantization. So here is, we talk about uniform quantization first. So uniform quantization is a quantization process with uniform quantization interval. That means each level, the voltage, the range of voltage between them are all having the same interval. All of the levels are balanced in terms of the range of voltage. So there are two types of uniform quantization here, which is mid-rise type and then mid-thread type. So the difference between them is, in the mid-rise type, if you focus on the origin, you can see that the origin lies in the middle of the rising part. So this occurs when the n is even, when the number of bits that we use is even. And then for mid-track type, focus at the origin will lies in the middle of the track part. So this is usually occurs when n equals to odd. So as we apply quantization, there is also an error will occur, which is called quantization error. This quantization error can be also called as quantization noise, QN. This error usually occurs when we change the continuous signal into discrete levels, and it behaves just like a noise added to a signal. So the maximum error is given with equal del over 2, which is equal to the quantization interval over 2. And there is also another formula, which is the quantization error to noise ratio, which is SNR cube, which is given SNR equals to 1.76 plus 6.02 n dB. N is the number of bits. So this is unfolded uniform quantization. So as we know, quantization level is L equals to 2 power n. So here there are mainly two formulas, which are binary code to voltage conversion, and then another one is convert voltage to binary code. So if you look at the first formula, binary code to voltage, so it is given voltage equals to VKL plus X multiplied by delta V. So VKL is the quantization value for the lowest value, for the lowest level. And then X will be the decimal value for the binary code. And then delta V will be the quantization interval. If you look at the second formula, voltage to binary code, it is given X equals to voltage minus VKL over delta V. So this is just rearranging the formula above until we get the term X from the previous formula. So these are the two formulas basically just for conversion between binary code and voltage. Here is an example about unfolded uniform quantization. So basically this example gives us the V peak to peak voltage is equal to 32 volt, which means that the amplitude is 16 volt. And then it goes through the PCM system and the output is a 7-bit code. So to solve this question, we can first find the quantization level L, which is equal to 2 power n. N here is 7 because it says 7-bit code. So L equals to 2 power 7 and is equal to 128. So after we find the quantization level, we can now find the quantization interval. So quantization interval is equal to Vmax minus Vmin over L. And Vmax minus Vmin is equal to V peak to peak. So it's equal to 32 over L. So it's 32 over 128. So after we calculate, the quantization interval is equal to 0.25 volt. And then we also need to calculate the maximum quantization noise or quantization error, which is the quantization interval over 2. So it's 0.25 over 2, which is equal to 0.125 volt. So after we calculate all these things, we also need to calculate the quantization value. So because based on the formula before, we need to use VKL. So is quantization value at the lowest level. So the lowest level here is negative 16 because the amplitude is 16 volt. So the lowest is negative 16 and then plus with the maximum quantization interval, which is 0.125, and then we get negative 15.875 as the VKL. So and then we can now calculate the voltage value for any given 7-bit code. So let's say you want to calculate the voltage value for the bit code 1101101. So we use the formula VKL plus X times delta V. So VKL is negative 15.875 plus X. X is the 7-bit code, and then we change to decimal from binary to decimal. So for 1101110 the decimal value is 109. So X is 109 and then multiply with 0.25. 0.25 is the quantization interval. So and then we get 11.375. So the voltage value for the 7-bit code 1101101 is 11.375. So let's say you want to calculate another bit code. So let's say the 7-bit code is for this time is 011001. So the same thing also, it is VKL plus X times delta V. So VKL is negative 15.875 and then X is the conversion of the binary code to decimal. For this case is 25 and then multiply by the quantization interval and then we get the voltage value. So the voltage value is negative 9.625. Just now we discussed the conversion of binary code to the voltage value. So now let's say we want to find the binary code based on the voltage value we input. So let's say the same example as before, which is the V peak is 32 volt and then goes through PCM system and it outputs a 7 code bit. So now let's say we input 13.62 volt. What is the binary code? So we also use back the formula. The formula is X equal to V minus VKL over del. So we substitute all the values. X equals to 13.62, the input voltage, minus with VKL. So VKL is the quantization value, which just now we found is negative 15.875 over the quantization interval, which is 0.25. And then X we got is 118. But this is in decimal. We need to change it to binary. So we convert 118 into binary, which is 1110110. So let's say another example is we want to find the binary code for the input of negative 9.37 volt. So the same thing. So X equal to negative 9.37 minus VKL. VKL is negative 15.875 over quantization interval 0.25, which we got equals to 26. And then the 26 need to convert to binary code. So 26 decimal is equal to 0011010 in binary. Just now we discussed about unfolded uniform quantization. So now we discuss folded uniform quantization. The difference between them is that this folded uniform quantization will look at the first significant bit, whereby if the first significant bit is 0 means it's negative, and then if it's 1 means it's positive. And here are also some variable terms used, which is y equals to the decimal value of the magnitude bit, z equals to the decimal value when all magnitude bits equals to 1, and then there is also vkl and vkh. Basically, vk is quantization value. So VKL is at the lowest and VKH is at the highest. So here are the formulas for folded uniform quantization. So let's say the significant bit now is 1, which means it's positive. And here there are two formulas, which is the same as before. Binary convert to voltage and then voltage convert to binary. So we see binary convert to voltage first. V equals to VKH minus Z minus Y times delta V. And then voltage convert to binary is Y equals to Z minus VKH minus V over delta V. This is for the positive when the sign bit is equal to 1. And then for the negative is around the same, just that we change VKH into VKL. So for positive, we use the highest quantization value, and for negative, we use the lowest quantization value. So this is just the difference between positive and negative. Here is an example for folded uniform quantization. So we use back the example as we discussed for the unfolded as well. So this is the same example. V peak to peak is equals to 32 volt, goes through PCM system and output a 7-bit code. So the values, the terms that we calculate before, L quantization level equals to 128, quantization interval equals to 0.25, and the maximum quantization noise is equal to 0.125. And VKL quantization value, lowest quantization value is negative 15.875. So now we want to find the voltage value for 1101101, the 7-bit code. Because this is folded uniform quantization, we need to look at the significant bit. So for 11011101, the significant bit is 1. The first value is 1. So it means that it is positive. So if you remember the formula before, to find the voltage value, the formula is VKH minus bracket Z minus Y, and then multiply by the quantization interval. So VKH for this, because it's VKH, H stands for highest quantization value is 15.875. The negative 15.875 is VKL, lowest. The highest is the positive 15.875. And then Z is the value when all bits are equal to 1. So this question is 7-bit code. But because we look at the significant bit, so 7-bit code, the first bit is just for the sign, and then the rest of the bits is what we need to consider for. So Z is the value when all bits equals to 1. So Z is equals to 111,111,61. Doesn't need to include the most significant one because that one is just for sign. So 111,111,61 is equals to 63 if you convert from binary to decimal. So Z is equal to 63 and then minus Y. Y is the current value for the 7-bit code that you insert. So same as before, you don't need to consider the first significant bit because that one is just for sign. So we just only take 101,101, which we convert into 45. And then we multiply by the quantization interval 0.25. And then in the end, we calculate the voltage value, which is 11.375. So if we now want to calculate the voltage value for another code, let's say this code is 011,001, and then the same as before, because the first significant bit is 0, means that it is negative, so we need to use the formula VKL plus Z minus Y multiplied by del. So VKL is equals to negative 15.875 plus Z. Z is the same, 63, and then minus Y. Y is 11001. Don't need to look at the first significant bit because that one is just for sign. And then multiply by quantization interval 0.25. And then in the end, we got negative 6.375. Now let's say we want to find the code when we input voltage. So now we input a voltage of 13.62. If we want to find back the code, we need to find the Y value. So because this is positive 13.62, if you remember the formula before, for positive, the formula is Z minus VKH minus voltage over quantization interval. So Z is 63 minus VKH 15.875 minus voltage, which is 13.62 over 0.25 quantization interval. So we got 54 in decimal, and then we need to convert 54 into binary, which is 110110. Here we need to add the significant bit by ourselves because the input voltage here is positive. It's positive 13.62. And if it's positive, means that the significant bit is 1. So we need to add 1 in front of our answer. So the final answer will be 1110,110. So now there is another example, which is we want to find the code for the input negative 9.37. So same as before, if you remember the formula is Z minus V minus VKL over quantization interval. Z is 63 minus V minus the voltage negative 9.37 minus VKL negative 15.875 over 0.25 quantization error. And then we got the answer is 37 in decimal. So Now we need to change 37 into binary, and then we need to add an additional 0 in front because the input is negative 9.37. It is negative. So negative means the significant bit is 0, and remember to add the 0 in front. Just now we discussed about uniform quantization. So now we discuss about non-uniform quantization. So because it's non-uniform, it means that the quantization interval is not constant. So this type of quantization is usually used when we have the sampling signals that have both weak and strong amplitudes. So it's hard for us to make the interval constant, the gap to be constant, because there are weak, there are strong amplitudes. The change is very much. So that's why we need to apply non-uniform quantization. So this non-uniform quantization can also help to improve the signal to noise ratio. And then in order to create this type of quantization, the process of compending is undergo. Compending is a process which is used in digital system where it reduces the data rates and improves the signal quality. So compending has many stages, mainly compress and then goes to uniform quantize and then we expand. So firstly, when we receive the analog signal, it will go through a nonlinear compressor. And then the signals that has small amplitude will be expand and the signals with large amplitudes will be compressed. So after the compression, the signals will go to a normal uniform quantizer. So at the receiver, the opposite function is used to restore the original amplitudes. Here there are two types of compending, analog compending and digital compending. So analog compending is done before ADC. ADC is analog to digital converter, while digital compending is done after ADC. And then analog compending uses hardware like diodes and transistor, while digital compending uses software like mu law or A law. Compending helps to produce uniform signal to noise ratio for all input range. Here is the formula of signal to noise ratio for non-uniform quantization using mu law. Now we look at some popular compending system. Like I mentioned just now is A law and mu law. So this is the formula for it. So this is the graph. The x-axis is the input and the y-axis is the output. So to find the value for y, here are the formulas given. So if you use A law, we have A equals to 87.6, which is fixed. If you use mu law, and we have mu equals to 255. So these are the formulas to find x and y. Here is a simple example about the compending system discussed about mu law. So the example says a compressed expand system using mu law with mu equals to 255 constant is used for a signal with range 0 to 10 volt. Determine the output of the system if the input is 0 and 7.5 volt. So the solution will be, we have two. So the first is input equals to 0 volt, EI equals to 0 volt, and X equals to EI over EI max. So EI is 0, EI max is 10 from the range there, 0 to 10, the maximum is 10. So X equals to 0 over 10, which is 0. And then we calculate for the Y. Y is given with the formula Y equal to log 1 plus mu X over log 1 plus mu. So we substitute all the value inside, and in the end we get y equals to 0. So for another input voltage, 7.5 is also the same thing. X equals to 7.5 over 10, and then we got x equals to 0.75, and then output y equals to log 1 plus mu x over log 1 plus mu. So we plug in all the formulas y, and then in the end we got y equals to 0.9 948. So this is just a simple example of discussing about the mu law compending system. So after quantization, the next step will be encoding. So basically encoding is just to convert each of the level, each quantization level that we got into binary code, because digital communication systems need to read binary code, can only read binary code. So we need to use encoding here. Here is the basic explanation for encoding. So after quantization is encoding. So let's say from sampling, we have four samples, and then from quantization, we understand that each samples belong to which level. Let's say sample one belongs to the third level, and then level 7, level 1, and level 4 for the next few samples. So after that, we need to change all these levels into codes in order for the digital systems to understand. So we need to decide how many bits that we need to use. If let's say we need to use 3 bits, then the first level, level 0, will be 000, 3 bits. And the last level, which is level 7, will be 111, which is also 3 bits. So this is how encoding works. Here are some applications of PCM. So PCM can be works in digital telephony, whereby PCM allows encoding voice message and digitalize for transmission over the network. PCM also works in digital system, where it captures high resolution of digital data for streaming and broadcasting. In space communication, also, PCM allow long-distance digital communication, which overcomes noise in analog system. In medical imaging, PCM utilized in ultrasound system in order to capture and process data that is needed. So after we discuss about PCM, there is a general misconception to the society who understands PCM in the wrong way, where the general misconception is that PCM is a type of modulation. But the truth is, PCM is not a type of modulation techniques, but more to analog to digital conversion technique. Another misconception is that people say PCM is a compression technique, but for the actual case, PCM is not a technique of compression, as the whole sampling is process is a lossless process, which the quality will be conserved. In fact, PCM acts as the foundation for the compression techniques such as mu law and A law only. For health-related misconception, people say that PCM can cause harmful radiation. But for the actual case, PCM is just digital data. It does not produce any radiation by itself. Another misconception is that high bit rate PCM audio can damage hearing. But the actual case is PCM only controls accuracy of sound, not loudness. For safety-related misconception, PCM failures can cause dangerous equipment faults. But the truth is, a corrupted PCM payload does not physically harm the equipment, it only affects the data accuracy. Another misconception will be PCM video or audio cables can cause electric shocks, but the actual case is digital audio cables carrying PCM operate at low voltage and it is safe for handling. We come to legal misconception, and there is a misconception of PCM audio or radio is always free to use, but actually the PCM method itself is open and not patented. Another misconception is PCM can guarantee privacy, but actually PCM digitalizes signals but does not encrypt them. Lastly, for environmental misconception, PCM reduces electronic waste because it is digital. But in truth, e-waste depends on the hardware lifespan, not the modulation technique. Another misconception is that digital PCM systems have zero environmental impact. But the truth is, digital systems also consume energy and it can contribute to carbon emission as well. In conclusion, PCM converts analog signal into clear and reliable digital data using sampling, quantization, and encoding. It is widely used because it provides high quality and strong noise resistance in modern communication systems. So this is the end of the video. Thank you for your time in understanding pulse code modulation, and we will catch you up